Okay, so I'm about to try and bring you in the inner sanctum of, moon math. And I was thinking for a long while, how can this be, what's a good way to try and show a little bit about what's going on? So first I'm going to apologize to all those who, work and know about proofs very deeply, because I'll be doing a lot of gross simplifications. But I do hope to talk a little bit about the role of low-degree polynomials and the way they lead to succinct checking of statements about computational integrity, and even to show you how zero knowledge is added into the picture. So how can you succinctly check statements with zero knowledge about large computational integrity statements, okay? And the hope is that by discussing these things, and I'll try to do it interactively or ask a lot of questions and see if there are answers, I hope that if you get into implementing them or reading papers about them, this will sort of give you some intuition. So arithmetization, it's a long word, it means the use of low-degree polynomials to argue about computation. And this is a very beautiful and old and immensely powerful technique, mathematical technique, that goes back even to the famous incompleteness results of Gödel from the 1930s. It's very influential, started in computational complexity with the work of Alexander Razborov in the 1980s, and brought into the context of proof systems in the later 1980s. I think it starts with Babay and Fortnow. And I want to show you how arithmetization works and how it leads to proving succinctly statements about very huge objects. So just a brief introduction about polynomials. So a polynomial is a formal sum of exponents. Examples are things like 5x plus 1, so it's a line. That's a polynomial. It's a polynomial of degree 1. Or the parabola, right, like x squared. Right, y equals x squared. That's an example of a polynomial of degree 2. And there's a x cubed, which looks a little bit like this. Good. So we have this formal sum, and its degree is the maximal non-zero term. And it's you can think of a polynomial as a program that you plug in x, and you get out the value, right? So it's a formal sum that sort of tells you how to compute stuff. But sometimes you also have like lookup tables or functions that, for every input, they already specify the output. And we'll call these functions. So a function has a certain domain, where is the lookup table looking at, and there's the values. So let's say our domains later on are going to be the numbers 1 to a billion, and we have a function that for each number between 1 and a billion gives a certain value, let's say a number. And we will say that such a function is a degree D function if it is the lookup table or the evaluation table of a degree D polynomial. So for instance, if the sequence is 1, 2, 3, 4, 5, so f of 1 equals 1, f of 2 equals 2, f of 3 equals 3, f of 4 equals 4, is this, what degree polynomial is this? It's a degree 1 polynomial. It's the polynomial f of x equals x. And if it would have been 1, so f of 1 equals 1, f of 2 equals 4, f of 3 equals 9, this would have been the polynomial. Right, the degree would be 2, and the polynomial would have been x squared. Good. But of course, you can do a lot more. You could do like x squared minus 5x1, sorry, x squared minus 5x plus 20. And I don't know what the table would be for that. Okay. Good. So a function, one of these lookup tables, will be said to be degree D if the polynomial that corresponds to it is of degree D. And you should think of D as sort of small. And here's a very useful fact that I won't prove. Well, we could prove it about lines. So we know that two lines, if they're not the same line, they will intersect at most at a point. And maybe in high school you also saw that two parabolas, if they're not the same, they will intersect in at most 2 points. And this generalizes. So two distinct functions that are of degree d, if they are not the same function, they will share at most d points. And this is a very powerful observation because it means that if you have two distinct functions that are of relatively small degree relative to the size of the lookup table, they will necessarily be very far apart. So for instance, and this is the example we're going to stick with, suppose the function is of degree that is 1% of the domain size, and sort of these are the objects that we allow in our universe. So we know that two such functions, if they're not the same, they will disagree on on 99% of the values, which sort of means that you can poll them or sample them at random and know if they're the same or different, right? And with 99% probability, if they're different, you will see that they are different. And this is a fact that we'll use, okay? And I want to emphasize that it's not about the degree, it's about the rate, the rate or the ratio between the degree and the domain size. So, okay. So think of D as pretty large. Later on, D is going to be 1,000, and the size of the lookup tables is going to be 1 billion. But still, two functions that are of degree 1,000, evaluated on 1 billion points, they, with very high probability, their entries won't agree on a random location. And this was already observed to be very useful back in the 60s, first by Reed and Solomon in the 1960s, who said, oh, this could be a really good way to store information and to relay it across noisy channels in a way that you can recover the information. So in the 1960s, they observed these things. Back then, there weren't, computers weren't very powerful and was very abstract and theoretical. And fast forward to 1995, Reed-Solomon codes start appearing in things like CDs and DVDs, so like 35 years or so, 3 decades. And it's interesting that this span is also sort of seems to be happening now with zero-knowledge technology, that like in the mid-1980s, there were constructions, and now we're in the teens, right? So I think it's 30 years later that they're starting to be implemented, right, in large scale. Okay. So let's start talking about computational integrity. And what we would like to do, the goal is something like this. So we would like for an arbitrary program, written in C, and some input, and a time bound, let's say 1 billion steps, Bob is claiming that the output of the program, including auxiliary information that he's not revealing, leads to a certain output, 7. Okay, this could be, this could be like the amount of Zcash that is unspent and, referenced in some anchor in the state of the system. So he has 7 coins. So this is an example of a program. And we would like to achieve, using polynomials, 3 goals. Integrity, that we would like to know that the answer is really 7 and not 2. Privacy, without leaking the auxiliary information, like all of his payment keys. And we would like to do this succinctly. So we would like the whole process, especially on the part of whoever is verifying the proof, to require much less than t cycles, where t is the number of steps it would take to check this or run this program. That's what we want to do. Now, let's scale down significantly and talk about a very simple kind of computational claim that could appear in some bigger computation. So Bob's claim number 1 is this. He says, there's a list of 1 million numbers, right, 10 to the 6 numbers, and they could be arbitrary, but my claim is, Bob is saying, that all of them are in the range 1 to 10. And Alice would like to check this thing. She doesn't know if it's true or not. And this is important because maybe it's part of a computation. But she would like to do only 2 queries to this list. So is it possible? Zuko is not. You're right. It's not possible. What?
That's not enough queries.
That's not enough queries. How many queries would Alice need?
Like 500,000?
She wants to know, I want to emphasize, she needs to know that all of them are in the range 1 to 10. So like if, if she queries half of them, or actually if she queries 999,000 and, she could still get it wrong, right? Because maybe the last, or, the one she didn't check could be not in this range, right? So, okay. So Bob is saying, yeah, Alice, I want to help you. I want to make things simpler for you computationally. So because I know that these polynomials add a whole lot of redundancy, here's what I did. I took these first million numbers I claim are all in the range of between 1 and 10. So they're like sitting, of all possible numbers, they're sort of in this band. And now what I did is I figured out what is the polynomial that evaluates to them, these 1 million numbers. There always is a polynomial of degree at most the number of entries in the list. So Bob is saying I already went ahead and computed this polynomial, and I am now writing a list of length 1 billion that is the evaluation of that polynomial. So what I'm doing is I'm using an error correcting code to add a whole lot of redundancy. And now, Alice, I hope this is going to make things a little bit easier for you because there's so much redundancy. And we repeat the question, can Alice check now with 2 queries and solve the problem? So now it's a list of length 1 billion. It's the original list, but it has a whole bunch of other entries that are related to those. Can she check it with 2 queries? So it's not so, does anyone want to venture a guess or? What? Yes. The answer is yes. Well, not yet. And it's actually the same problem as before because Bob could take the very last entry, or he could toss some coins, pick an entry somewhere in the middle, make that entry 11, and then take this whole sequence and encode it using a polynomial. So you would get this sequence that is almost okay. There's one entry that's bad, and it would be some evaluation. It would be impossible to glean from 2 queries, any 2 queries, whether this is a good list or a bad list. So Bob is now getting frustrated, and he comes to Alice and says, okay, what more would you need from me? What do you want? And here's an amazing thing, if you haven't seen it before. So Alice tells him, you know what, Bob, here's what you can do. I'd like you to evaluate for me 1 more polynomial. Let's call it g. So it's going to be another function evaluated on 1 billion points. And its degree is going to be 10, it's going to be like 10 million minus 1 million. So I guess that's 9 million. So, it should be a degree 9 million polynomial. And I have already a test that I will show you in a minute. And I'm going to query 1 random location in both f and g, and that's all I need to know. And now I will know with very high certainty, 99% certainty, whether the original list has all numbers in the range 1 to 10 or not. All of them. Now you're wondering, oh, this is some kind of magic. How can it be? Yes, of course, it's magic called math. So let's see now, what's the test? So now, okay, I'm going to explain now how the magic works, which is what magicians are not supposed to do. But, okay. So we're going to have to define 2 auxiliary polynomials. I'll call them C and D. C is going to be the constraint polynomial. It checks constraints. And D is going to be the domain polynomial. It sort of specifies where do you need to check these constraints. And remember that Bob has said, I have this function f that is evaluated on 1 billion points. And Alice wants to check whether it corresponds to a list that all the 1 million first entries are in the range 1 to 10. So the constraint polynomial is what you see here. It's x minus 1 times x minus 2 times x minus 3, so on and so on, up to times x minus 10. And it's not hard to see that this polynomial vanishes or evaluates to 0 on exactly 10 inputs. What are these inputs? Exactly, 1 to 10. Now, why? Because, okay, it's easy to see that it certainly vanishes on these inputs, because if you plug in a number between 1 to 10, one of these guys in the product is going to be 0, and 0 times any other number is still 0. Okay. It's not immediate to see that those are the only cases, but it's a fact. So we have now a polynomial that is the constraint checking polynomial. It is the thing that checks whether a number is in the range 1 to 10. So it's like a fancy way of checking for a particular entry whether it is whether it is okay. The other polynomial is this domain polynomial. And it's a much larger size polynomial. And it's exactly the same kind as C, but it vanishes on 1,000,000 points, on the points 1 to 1,000,000. So it's defined the same way, but it just goes, it's a product of many, many, many more terms. And you can open everything up, and you'll get some polynomial written as a formal sum. C is of degree 10, and D is of degree 1,000,000. So Alice explains all of this to Bob. She's telling him, listen, these are these two polynomials. They're what I'm going to be working with. And here's my test, Bob. I'm going to pick a random element, x naught, in the whole range of 1 to 1,000,000,000. And then I'm going to make my two queries. The first is going to be to the function f that you claim is this good list, and it's encoding. And the second is to a polynomial g that is supposed to have degree 9,000,000, but you can write any polynomial of degree 9,000,000 that you want. I don't care, right? You can't change f. The claim is about f. But you can write any polynomial g that you want as long as it has degree 9,000,000. And now, Bob, so go down, write your polynomial. This is what I'm going to do. After you wrote it down, f is already written, g is now written. I'm going to toss coins. I'm going to pick my x naught uniformly at random. And then I'm going to query f and g at the same point, x naught. And then I'm going to believe your claim if and only if. So the answers, let's call them alpha is what you read at the point, from f. And beta is what you read from g. So Alice says, I'm going to accept your claim if this equality holds. And if it doesn't hold, I'm not going to accept your claim. That's it. Sorry? So C of alpha is a number. Basically, you do alpha minus 1, you multiply it by alpha minus 2, multiplied by alpha minus 3, all the way up to 10. You multiply these numbers, and you get a value. No, C is that polynomial. OK, here's a different way to explain how she's going to check it. She's going to read. She goes to the table. She goes to the function, this lookup table f. She looks at the point x0, reads an entry. The entry is not x0. It's whatever Bob wrote there. And she says, I'm calling this alpha. Now, what I do is, to compute C of alpha, I first of all do alpha minus 1, alpha minus 2, alpha minus 3, alpha minus 4, up to alpha minus 10. So I get a bunch of 10 numbers. I multiply all of them. And this is C of alpha. Yes, Vitaly?
So let's suppose that Bob chooses g equals 0. So then that formula is going to collapse to C of A equals 0.
Right.
Now let's say that Bob does provide a legitimate answer.
A what?
So let's say Bob does provide a legitimate answer. Then Alice chooses x0, which is greater than 1,000,000. Then we'll say that most of these functions that return numbers between 0 and 10.
Oh, wait, let me stop you. An honest Bob has only one way to choose the right G.
Oh, okay.
And we'll see it in a minute. So you're saying something that's very true. Even if f is correct, Bob may give a bad G, which won't pass the test. And this is actually something that happens in proofs. So there could be a true claim, and you could, maliciously or by mistake, not provide a proof for it. And I think what you were heading toward is one example of that. So all we need to show is that, and we'll get to it in a minute, we will show that if f is good, there exists a G that satisfies. And if f is not good, then all G will fail. OK, but let me first of all explain how this test works. So first of all, notice that even though we have these two huge tables, Alice really reads only one entry from each. So she's true to this constraint. And they're huge tables, and they talk about huge objects, right? Polynomials of degree 1 million written over a billion steps. But she reads only one entry from each. And the computation is, so I explain how you compute C of alpha, right? You get basically 10 numbers derived from the value alpha. You multiply all of them. You call that C of alpha. Then for beta, you do the same thing, but you have to run for 1 million steps, right? Which is kind of, takes a lot of time, but let's not get into that, okay? And then you take that and you multiply it by d, oh, sorry, no, yeah. D at the point x naught would take Alice 1 million steps to check, right? Because she reads x naught. I mean, she doesn't need to read x naught. She picked x naught, and she plugs it into this product d. So she does x naught minus 1, x naught minus 2, x naught minus 3, and then x naught minus 1 million. Take all of their product, that's some number, multiply it by beta, check if it equals. That's the test. Boom. Good. Now, the interesting part are the completeness and soundness. And I just want to tell you that all of these concepts that we're discussing actually appear in all the research papers that talk about things like zero-knowledge proofs. There's going to be a completeness statement, there's going to be a soundness statement, and they're going to look something like this, but usually they're a little bit more complicated. So here's the test. And now we're going to first talk about completeness, which is the easier case. So suppose Bob is honest. What does it mean? It means that the polynomial P of x that is really the description of f is a good one. It really evaluates to between 1 to 10 on all numbers between 1 and 1 million. Now, if we plug this polynomial as an input to the other polynomial, we get something that vanishes on the first million entries. Why? C is a polynomial, something that if it receives a number between 1 and 10, it spits out 0. And P has this property. It is something that gives you only numbers between 1 and 10 on the first million entries. What happens afterwards is, we don't care. So C applied to P of x really does vanish on all the domain. Okay. And here's a fact that, again, you may have learned in high school or university, and it's a general fact about polynomials. Q of x vanishes or evaluates to 0 at a point x naught if and only if you can factor it and break it up into the product of two simple things. If and only if there exists a polynomial q prime, which has degree slightly less than q, 1 less than q, such that the polynomial q of x equals this form. It's a simple polynomial, x minus x naught times q prime. And this is a basic fact about polynomials. For instance, here's an example. A line, so it's a degree 1 polynomial, vanishes at the point 0, so it passes through the origin, if and only if it is of the form x times something, right? Okay, so x divides it. It's going to be x times a constant. And this is more general. So a polynomial vanishes at 0 if and only if you can write it as x times some other polynomial. So like a parabola would also vanish at 0 if and only if you can take x outside. And similarly, a polynomial vanishes at the point 1 if and only if you can write it as x minus 1 times a polynomial. And if you continue on and sort of take all the roots out, all these places where you vanish, then here's a corollary that says that q of x, let's define q of x as c of p of x, it vanishes on all of the domain, all of the first million entries, if and only if there exists some q prime, and its degree, the degree of q prime is the degree of q minus the size of the domain, which is exactly 9 million, which is what Alice is going to allow Bob to write in G, such that q of x equals q prime of x times d of x. By the way, the prime is not derivative. It's just some other polynomial. So what does Honest Bob do? Honest Bob computes Q prime of x, which must exist, and he just evaluates that. Let's just see what happens. When Alice picks x naught, and she reads P of x naught and plugs it into this C thing, so you get C of alpha, it equals Q of x naught, because we just defined Q to be P, C of P. Q is just C of P. So this is equality by definition. But because of the fact, Q of x can really be written as Q prime of x naught times D of x naught. And Bob, Honest Bob, called this thing G. So this is the value beta. So the test passes with probability 1. There's no error. So if Bob was honest and he gives the right G, the test passes with probability 1, even though there are only 2 queries. Good. In all proofs about proofs, so proofs of zero knowledge or proofs of other interactive proof systems, the harder part is always soundness. And soundness is the case of malicious Bob. So let's deal with that now. So we have the same test. And now we're supposing that Bob is cheating. So for instance, we have some, let's say the first entry has the value 11. It could be some other random entry. So Bob is cheating. This is not, he's making a false claim, even though he's just cheating at 1 entry out of 1,000,000. Let's see that Alice is going to catch him with probability 99% with only 2 queries. So the function f has an interpolant. There's a polynomial that describes it. Now, if you look at C of P of x, it vanishes almost on all the domain, but there is one point where it doesn't vanish, point 1, right? So C of P of 1 will not equal 0. It will be some other number. But for any other polynomial that G is supposed to be its evaluation, if you look at Q prime of x and multiply it by D of x, by the domain polynomial is selected as to vanish on all the first 1,000,000 entries. And once a polynomial is vanished, if you multiply it by something, it's still 0. So this, the right-hand side of the test will be 0. So that's what's written here. For any low-degree polynomial of degree 9,000,000, this polynomial that is actually appearing on the right-hand side is distinct. It's not the same polynomial as the left-hand side. And now we go back to the fact about the distance of polynomials. And we know that 2 polynomials of degree d, if they're not the same, they can agree on only d many points. But we have a domain of size 1,000,000,000, and we have 2 polynomials that are less than, their degree is less than 1% of that domain size, so they will disagree on 99% of their entries. And that's why soundness also follows. So if it's not the same polynomial, the probability that Alice will reject is at least 99%. So that's soundness. Now this, in essence, is what goes in to SNARKS and STARKS and the Ligero system I mentioned, and a whole bunch of, and Pepper and Zatar, and in all of these things, you have such phenomena underlying soundness and completeness. It's okay. So the point is that if Bob uses only low-degree polynomials, then Alice can check the claim about list range integrity for arbitrary size lists with only 2 queries and 99% probability. So we achieved succinctness. But maybe this was, maybe it was some special case. What about we want to check computational integrity? We have a program that we want to know is correct. Well, checking a program, you could sort of, its execution, you could list it down as an execution trace. It would be a sequence of numbers that describe the state of the machine. So we're almost in the same problem. Execution trace is already a list of numbers, and the trace is valid if and only if each pair of consecutive states satisfies something related to the program. So what is this thing that must be satisfied? Well, you could express it with a polynomial. So for instance, here's a simple program. It's a program that only increments. So it does +1, let's say for 1,000,000 steps. It starts with a value 5, and at each step it goes, +1. So we expect this, its execution trace is supposed to be 5, 6, 7, 8, up to 1,000,000 + 5. But there is a constraint that is this very simple polynomial. It checks that the next value is equal to the current value +1, and it corresponds to checking the computational integrity of the program. So instead of using the previous constraint polynomial that only looked at a current state, let's use a different polynomial with two variables that compares the two entries or the two states, consecutive states. And now we could, in the same way, we could prove claims like this list is the execution trace of the incrementing program. And you just need to change your constraint polynomial. Previously, it just checked a range, or actually a type of a variable, right? Checking that the variable has has range between 1 and 10 is a type checking constraint, which is very simple. Now we have a more complicated constraint that checks two consecutive states. But the test of Alice is almost the same. She's going to need to make 3 queries: an entry, the next entry, and something from G. But it operates in the same way. And the same analysis gives you perfect completeness and soundness error less than 1% for exactly the same reasons. Good. So the summary is that the query complexity doesn't really depend at all on the running time of the program, which is absolutely amazing and wonderful. And in fact, the soundness error depends only on the number of queries you're making and on the code, on the rate of the error correcting code, on the ratio between the degree of the polynomial and the number of evaluation points. Cool. And now you're thinking, okay, maybe it works only for this program. Well, if you have a more complicated program, it means the state is going to be some huge number, and checking consistency of 2 consecutive states is going to be some higher degree polynomial that is more complicated, but it still is the same game. And we still have the same succinctness and the same completeness and the same soundness as here. It's all the same. And again, these things appear in all zero-knowledge and interactive proof systems that have been implemented out there. Okay? What about zero-knowledge? So Bob is now claiming, well, I have this list that's the execution trace of a program, but I'm not going to show you the execution trace because it contains a password or my Zcash address. But I want to prove to you that the answer is, the output is 7. So the point is that the test that Alice was doing didn't have any particular preference to the first 1,000,000 numbers where the important payload and private payload may exist. So Alice would be perfectly fine limiting her choice of x0 to only the higher numbers that don't actually touch the first few entries. And then there's another simple addition. Okay, it's simple to state. Proving it I'm not going to go into it. But here's what is actually done. Alice tells Bob, you know what? I respect your privacy. So instead, I know you could give me a polynomial of degree exactly 1,000,000 that would represent your execution trace, but to preserve your privacy, I'm going to allow you to use a polynomial of degree not 1,000,000, but let's say 1,000,000 plus 10. Okay, you're allowed to do that. And then I'm going to do all my tests in the same way. Now, this allows Bob to start with his execution trace and append to it 10 random numbers, completely random numbers. And the funny thing about polynomials is that no matter what you write in the first 10 entries, in the first 1,000,000 entries, if you add 10 random numbers, and then Alice comes around and reads any 9 numbers from later on, she will see random numbers, meaning no matter what is written in the first 1,000,000 entries, so for any fixing the first 1,000,000 entries, let's say all zeros, if Bob now picks at random 10 numbers and fills the next 10 entries, and Alice goes and views at random, some other 10 entries, Alice will see uniformly random entries. So like the experiment is, Bob is like randomizing these 10 numbers. He's not changing the first part. And Alice goes and checks it, and she sees completely random stuff. So we have this notion that is very similar to what happens in Shamir's secret sharing paradigm, where the information payload didn't really change, but you have this auxiliary randomness that makes everything zero knowledge. And Alice's test, the only modification is she respects Bob's privacy and she doesn't read from the first million entries. And now everything works, including zero knowledge. Okay, good. So this is the summary. We saw that arithmetization, taking statements about computation and extending them using low-degree polynomials, gives you a way to succinctly check arbitrary statements about computation. And if you allow a little bit of randomness, if you allow the prover a little bit randomness and a little bit of extra degree in the value of this polynomial, in degree in the polynomial, you even get zero knowledge. And you actually get the strongest form of zero knowledge that's called perfect zero knowledge, which means that actually what Alice ends up seeing are completely uniformly random numbers. Okay, so it's, yeah. Okay. So to summarize, again, arithmetization allows you succinctness, extreme succinctness, and computational integrity, and with a little bit more randomness, you also get zero knowledge and privacy, the strongest form of them. Okay, now what we didn't see is, and this is the real source of pain and of extra computational complexity requirements, is how do we prevent Bob from being completely dishonest and not writing down an arbitrary function that is not the evaluation of a degree million polynomial? That's the real challenge. And part of what makes it hard is that for any million values in the first, in the first million, for any filling of the first million entries, there is a degree million polynomial that actually interpolates them. So this means that Alice needs to read at least 1,000,001 entries to even know if this is a degree million polynomial or not. So Bob, the way we described it so far, could cheat by not giving degree D polynomials. And all of our analysis of soundness depended on the fact that degree D polynomials, if they're not the same, they're very far apart. So if we can't prevent Bob from using only degree D polynomials, he can really muck things up. So the big challenge in all of the proof systems that you are aware of has to do with preventing Bob from using polynomials of higher degree than what Alice agreed to. This appears in all of the proof systems out there. And they're very roughly and very, informally speaking, there are two kinds of main solutions. One, pioneered by Yuval Yishai, Eyal Kushilevitz, and Rafi Ostrovsky, says, well, let's throw in some heavyweight cryptography in order to achieve two things at the same time. This cryptography will allow Bob to evaluate any polynomial of degree D, but only polynomials of degree D, and he will evaluate them at a point x naught that is unknown to him. Again, the first solution says we use cryptography to hide x naught from Bob while allowing him still the ability to evaluate any polynomial of his choice at the unknown point x naught. And this needs something known as additively homomorphic encryption. It actually needs a little bit more for it to be, a proof system. And the second method is to use things like PCPs, probabilistically checkable proofs, that goes back to the 90s, and a commit-reveal scheme, where you use things like, you use extra algebra in order to tell Bob, you know what, you can write whatever you want under F and under G. But you're also going to give me some extra information on top of that. And these things are proofs. And you're going to commit to all of this. And then I'm going to make a small number of queries to all of this information and solve the problem. And these things are known as low-degree testing solutions, and they will be the topic. So the low-degree testing problem, which is the only remaining problem in this line, will be the discussion of my next lecture. And I just want to say about, because there's SNARKs and STARKs, and I mean, again, simplifying things, at least, I've been associated with SNARKs and STARKs. So to me, solution number one, because you're going to hide x naught, you need this, there's some trapdoor, and the trapdoor is x naught. So if you remember, those who attended Zuko's lecture, he talked about the g to the tau. So his tau is this x naught, and it's hidden in a way, and Zcash, so listen to the ceremony episode from Radiolab, and when they talk about the secret and the toxic waste that needs to be encoded, what they are talking about hiding or preventing from getting out there is what I'm calling x naught and what he called tau. It's all about preventing this to be known, because if it's known, there are ways to make bad things happen. And the other solution is transparent and leads to things like ZK STARKs and also many, many other solutions, such as, again, the Ligero system that I mentioned. So that's the first part of my talk. And in the next part, I'll tell you a little bit about the way low-degree testing is done in the new system in STARK.